you're going to spotlight me and then I hope your host, right, AJ? Yeah, okay.
Your spotlight, and it started.
Okay, cool. So, hi everybody. I missed you. Good to see you again. So, we're just doing a mini lecture today, but following up on the lectures you just saw on stochastic dynamics, right? So I hope that you, I mean, I really think there's something very, very beautiful about thinking about what happens when you take a distribution, entire distribution, and start pushing it through a nonlinear system, right? So I think the image of what happens even for the van der Pol oscillator, how these distributions will run around the limit cycle and then spread out. You know, I really like the example of how the distributions work for the rimless wheel, to think about some of the implications of how that works in hybrid systems. But that, you know, that first lecture was hopefully just to get you thinking about the beauty, the complexity of not just pushing a single state through a system and getting a trajectory out, but taking an entire distribution through a system and pushing that distribution. And there's really a lot to know about that, right? So, I mean, and you might have seen it in other places, right? Like statistical mechanics folks talk about this. You'll hear, you'll see connections there to Liouville theorems and Perron-Frobenius and all these things that you might have heard in different places. That it's all the same stuff. It's about how do you take a distribution and push it through a dynamical system. And our dynamical systems maybe are cooler, more structured than most, but you know, than like a box of gas or something. But but otherwise, it's really the same kind of math. So the second part of that, you know, and it seems kind of crazy to me, you know, to say like, okay, we're going to just talk about stochastic and robust control, which are both like by themselves big topics. So I just want to land, you know, a few of you gave me nice feedback, right? Where it's nice to have seen the lecture and then just see a little bit of kind of, let me say it again in a slightly different way, add a little bit. So that's what I'm going to try to do. I'm going to try to say the same thing sort of again, but maybe make sure I land at least the core idea behind the robust control. So you have that going forward and you have the references and everything. So even for linear dynamical systems, let's just make sure we connect the dots, because I've mentioned robust control a few times throughout the semester, right? And it's come up and we've said, okay, it's coming, you know. So let me just try to pull that thread through and make sure we've connected the dots. So we thought a lot about, you know, how do you do LQR, for instance, or different model predictive control, you know, all these different things we know how to do for the system. AXN+1 is AX plus BU, right? And we're really going to do a minor change, but it brings in all the beauty of stochastic dynamics. We're going to have W as a second input into the system. And I'm going to think of W as being a random input that's drawn from some distribution. And in general, we'll say that it's drawn independently on every time step. But that's just sort of for convenience. There's other ways to do that. And I even gave an example in the lecture about how you could take a system that is a white noise random input and just put it through a linear system to get a colored noise. And that was my model for wind when we did the balancing of the you know, the prop hang in the wind. So the balancing UAV in the wind. Okay, so so this is sort of the setup, and roughly speaking, you know, stochastic control refers to when you're trying to do things like reasoning about the distribution. Maybe you're trying to optimize a metric like the expected value of some performance criterion. And robust control is incredibly related, and they sit right on top of each other and use all the same tools. Robust control tends to be more about worst case analysis, saying that maybe W is bounded, or even if W is unbounded, maybe I can worst case bound the gain. We'll make sure we land that the gain from the random disturbance to the state or to the output. Okay, so stochastic and robust control. Now, where have we seen those before? So let me you know, take you back to the very first time I said anything about robust control. Do you remember this example in Lyapunov, right, where we talked about It was the first time I tried to motivate Lyapunov functions and robustness for linear systems, right? And it was even the first time I introduced semi-definite programming. The idea was that for a known linear system, there's a Lyapunov equation. We can find some quadratic Lyapunov function that will prove that a linear system is stable, and that's actually a pretty easy problem. You don't need optimization. You can just call the Lyapunov method in Drake or MATLAB. Okay. The more interesting case was if I have x dot is ax, you can see in this example here, x dot equals ax, but I don't know the coefficients of a, right? So a was, we had uncertainty about the coefficients, but we said that the coefficients were unknown, but they were in some convex set. In particular, in that example, I parameterized the set as the affine combination of 5 different A matrices. Right, so it's somehow some combination, and that is equivalent to making this sort of polytopic representation of the uncertainty. It's just one way to write it. And we were able to then say, well, if I can find a Lyapunov function, which is going downhill for A1, for A2, for A3, for A4, and A5, then actually it must also be going downhill. There was a couple steps of algebra to show that it must have also been going downhill for everything inside that red region, right? So that was an example, that is an example of robust control where we had uncertainty in the dynamics, and we were able to use Lyapunov functions to get around it. That's a slightly different example than what I just wrote on the last slide, where we have uncertainty in the input, right? Where we had a W as a disturbance input. Although, as we'll see, you can make those look the same with a standard robust control diagram. Okay. Any questions, reminiscing anything about this example? Remember that one? Okay, so from there, I actually did mention the idea. I'm sorry to scroll for a second here, but I mentioned in the context of our cubic polynomial, my favorite little sums of squares example, I mentioned that there's a subtle thing a more subtle thing that happens when you have additive uncertainty. Okay, so this was the nominal system. If I wanted to do a robustness analysis with common Lyapunov functions for the nonlinear system here, this is the sort of a nonlinear example, but corresponding to the same kind of uncertainty that I had in the previous example. So here I have basically a gain uncertainty. So it's like my A matrix here is alpha is my uncertain parameter. Okay, and as I change alpha, it might be uncertain. It might be between 3/4 and 3/2. In this example, it's going to change the slope of my linear dynamical system. I'm sorry, just one second. Sorry, my family was screaming. I wanted to make sure it was okay. I think it's okay. All right, so this is the equivalent to that A matrix being uncertain, right? So it's going to change the slope potentially, and I changed it modestly here, but we can still find a Lyapunov function that shows that the system is stable, right? So
I had a question about.
Yeah, please.
Yeah, I had a question about some of the vocabulary. So region of attraction and basin of attraction are the same thing, right?
Yes. Yes.
What is the relationship between region of attraction for a fixed point and like the backwards reachable set for the fixed point?
Oh, good. Yeah. So backwards reachable set and region of attraction, I would say, are the same thing in the limit where the backwards reachable set is taken to negative infinity.
I see. Okay.
Right. The backwards reachable set is a richer language in the sense that you can talk about finite time.
Mm-hmm.
Right. So if you had, for instance, I want to land in some target, and I want to say, like, when I'm 4 steps away from that target, what is my set that will land in that target?
Got it.
Mm-hmm. You can also, I think it's also richer in the sense that you can have a target where you typically talk only about getting to a fixed point in the infinite horizon case. Good, thank you for asking that, yeah.
Thanks.
Okay, so, but we can still be stable even though we're uncertain, right? We've seen that in those two examples, right? The box uncertainty for general linear systems, and this is a nonlinear system, but it's still stable in some region. It's different though when I have additive uncertainty. This is now, I've got it, some additive uncertainty, like I called it alpha before as my uncertain parameter, but think of it as a noise W in this lecture, right? So if I'm adding W in, then it actually means that I won't have a fixed point at the origin, right? If I'm adding additive Gaussian noise, for instance, right? It is not the case that I will get to the origin and stay at the origin forever. It is the noise will constantly bounce me around. You know, you'll have some distribution around the origin, for instance, even if it's a bounded set. I could have a bounded region, but I wouldn't necessarily, in most cases, I wouldn't expect additive uncertainty to permit us an argument about stability, right? So back when we talked about it before, I said, okay, that's okay. You can still give a discussion about an invariant set, right? So you can still say something like, well, I can't argue that I'm going to converge to the origin, but if I find a Lyapunov function that is going downhill at the boundaries, then I at least know I will never leave the boundary, right? If for all possible values of alpha, I'm going downhill at the boundary, then I'll never leave that boundary, right? But I wouldn't expect to be able to find a statement at the origin saying for all alpha, I'm going to stay at the origin. Okay, so that's a subtlety, but it is kind of the crux of what we're talking about in robust control. I think that's somehow a key idea if you want to understand H infinity control. And what I want to say today, and what I think I said in the video coming up to this, but maybe I can say directly in connection to this is true, this invariant set, but it's actually a very weak way to talk about the stability or the robustness of this system, right? So it's a very weak statement to say, if you bounded alpha, then I'm going to stay inside some bounded region, right? I think there's a much richer language that robust control uses, which still gives worst case bounds, but it talks about, instead of saying the absolute, what can I expect X to never leave, it gives a gain bound, right? So we talked about the proportion of basically, if W is bigger, you know, based on the size of the disturbance W, I'd expect that the size of the disturbance in X to get bigger. But I'd like that to bound the relative magnitude of those. So let me try to write that a little bit more carefully here. Right, so in the L2 gain worked in discrete time or continuous time. But what I'd like to say instead is somehow that if I take some, well, first I'll just write it as so if you think about X starting at 0, so 0 initial conditions, if W is completely 0, then and my system is stable, then I would expect X to stay at 0. But if I start adding noise, if I start having some amount of noise that I'm adding into the system, then I'd expect X to similarly bounce around. But what's a statement that we can make that is strong and is relevant for linear systems is that maybe I can bound the ratio of this disturbance. So in particular, if I say that somehow this is bounded by some scalar quantity like a gamma, okay, and I'd like to say that this is true for all possible W's, So for all w's where the integral is bounded, to be careful, I need to say that this actually lives in L2, otherwise things could get weird, okay? But basically, this value here is an integral over this, over the signal W. I'm just thinking of that as a signal coming in, right? And so you can think about this as the total power in the signal, right? If I had W that was 1 forever, that's an unbounded amount of input, and I could expect potentially, I'm not trying to cover that case. I'm saying that I have a random input, but the total power in that random input is finite, okay? But the bigger it is, the bigger I'd expect my response to be, up to some proportion. Now, why is that? Why is that a reasonable thing, right? So we know that the response of a linear system to any input is going to be a linear function, right? That's I guess the whole point of linear dynamical systems, right? So it makes sense that that asking for it to be inside some constant region, it's just kind of the wrong way to talk about robustness of a linear system. You're asking it to do something it's not particularly meant to do. It's much better for a function that takes some signal and multiplies it effectively by a big linear transform, right? To ask what's the gain of that transform, right? It's a much more natural description of the robustness of the system. Okay, and you can do that the same thing in discrete time, right? If you somehow, oops, I put the X on the wrong side here. Right, so that would be, I could take my linear system, which is some complicated matrix function, you know, of all my A's, and what we've written out sort of what happens to the state as a function of a series of inputs a few times in the classes. It's A to the n times x0 plus some combination of A's and B's for all the different summed over all the different U's. The same thing would be true here. But it's still a linear function. If I push W in, I get a linear some linear transform of W out. This is asking me to find a different system effectively, which is just a scalar function multiply of the W in to the X out, which is always bigger. The output is always bigger, right? The total power in the output is always bigger. And that's a scalar number that talks about the robustness of my system, of a potentially complicated system. And this number is called the L2 gain. And I think fundamentally, it's a more natural way for systems that tend to multiply the input. You should talk about a multiplicative statement about the robustness. Okay, so that was sort of idea one, was that generalized our notion of Lyapunov. And in the lecture, I showed you that there's a very Lyapunov-like argument on how to get this, where we went from a Lyapunov function to a dissipation inequality, but it was very, very similar. You find a Lyapunov-like function that can certify that you have some sort of L2 gain. But what I really want to make sure you get today is kind of how does robust control connect to this, and what is H2, what is H infinity? We've heard there's kind of the joke, which is that I think robust control is encrypted, right? You have to know all the secret codes in order to understand the papers, right? When there's a relatively straightforward idea in the paper, but it starts with like assume a Banach space and all, you're lost already, right? So I just want to land the simple idea, right? So I hope this kind of idea of bounding the gain makes sense. And here's this first piece of the secret code, okay? That we typically don't write this. This picture that I'm drawing right here is somehow I've got a W coming in, I've got a U coming in, I have X coming out. And that is true, and you can use that. But the richer language of robust control will generalize this to some performance output, they call it. Okay, so you'll have Wn coming in and Un coming in. You can have X coming out if you want for your controller, but we'll just make some other output Zn, which is sort of my performance output. It's basically, think of it as a cost function, but it's we'll show you that it's closely related to, for instance, an LQR cost function, but we'll choose it a little differently. So in general, I can ask about the L2 gain from any input to any output. And for a robustness argument, the standard thing we ask for is an L2 gain from W to Z, to a performance output. And here's the thing that I really think, mixes everything up in the language, right? People have observed, cleverly, that if I choose Z to be a vector like this, okay, which is just defined, this is the square root of my Q matrix that I would use in LQR, and the square root of my R matrix that I would use in LQR, then the total power when I write this, that's equivalent to my LQR cost, right? It's just a kind of another way to write the LQR cost. As a result, you can call LQR, if you want, you can call it H2 optimal control, because there's another way to think about it, which is you're kind of minimize the norm of a system. So we'll talk about the Hardy norms, but H2 optimal control or H infinity optimal control, they're talking about not the norms of a signal, but the norm of a system, which is a property of the transfer function, let's say from whatever input and output, but from W to Z. So it's super clever, super tricky, and kind of annoying in the literature, but you can write the LQR problem as saying, I'm going to optimize the H2 norm from W to Z. And that's an equivalent statement, okay? In fact, this is the stochastic LQR problem. So if I want to minimize the expected value of the sum of n x transpose qn plus u transpose ru, okay, and w is taken to be unit covariant Gaussian, and z is taken to be this function I wrote right here, then the H2 norm, which is the power, the H2 norm is the power in the impulse response of the system. Now, we haven't done significant thinking about impulse responses of linear systems and stuff, so I'm not trying to, that may or may not land for you, but if you want to know what it is, it's related to it's the power, it's defined as the power of the impulse response of the system. And what I really do want you to get is that H2 can often be just synonymous with LQR, or the stochastic version of LQR, okay? So that is, when you hear H2 optimal control, hear stochastic LQR, basically. H infinity optimal control is a different norm. It's the largest singular value of the transfer function is one way to say it. If you're a linear systems world, it's But again, that sort of doesn't, that's not the part I want you to definitely remember. What I want you to definitely remember is when you're talking about H infinity, you're computing the L2 gain. Okay, so this I hope makes sense, is the idea that you could compute that gain, and it turns out a different way to say I'm going to compute the L2 gain is like you're going to say I'm going to optimize the H infinity norm of the system. Okay, so it's hopefully slightly unencrypted, right? That's just, you have to, it takes like a lot of work to sort of connect all the dots and realize that that's just, they're saying the same thing. In the particular choice, in the particular case of choosing Z to be this form, W to be a Gaussian, you know, we showed in the lecture that you can solve a Riccati equation and find a controller K, which minimizes the H infinity norm, that becomes a problem that we can solve nicely. And that was the, you know, tweak on LQR that I gave you that gives you a robust control that minimizes the L2 gain. So let me pause. Does that help connect some dots or not? I don't know. I feel like everybody's heard of H infinity control, and it takes a lot of work to actually understand what it's doing.
Okay, I just want to clarify. So when you're doing H infinity optimal control, it's synonymous to minimizing the L2 gain? Optimizing the L2 gain?
Yes, I think that is true. The richness is that you could pick it for different you could pick your Z differently or your W differently and have a different interpretation. But I think it's always true that you're minimizing the L2 gain. And that's actually really important because there are other ways you might use it. You might not care directly about the LQR cost out. You might actually care about the gain between two parts of a system. So for instance, one of the other big ideas, which I mentioned quickly, and I try to just land again here, but let's say I have W and I have some Z, maybe it's not my LQR, but it's whatever connection I have to system 2. And then I have, let's say, Z2 coming out here. If I have an L2 gain from W to Z and from Z to Z2, then I sort of trivially have a gain from W to Z2, which is the multiplication of those two gains. That's one of the great things about finding an L2 gain number, is that you can compose systems very nicely. So that's a case where you might minimize the H infinity norm from W to Z in system 1, even if Z is not chosen to be an LQR objective, right? But you really just want to make that gain small because you know you're going to put it in composition with some other systems. And in this case, the bits of system 1 that system 2 is dependent on, may or may not be under your control, right? There's some coupling between those systems. And you can say, if I can bound the gain of this system, knowing that it's connected to this system and through Z, bound the gain of the second system, I can say something about the total gain of the total system. That's even more powerful if it's put in feedback loop. So this becomes sort of the beautiful control system, a robust control diagram you call W in, Z out. Okay, and you say this is my known linear system, let's say, and let's say delta is some unknown plant dynamics, unknown unmodeled plant dynamics. It takes more work than I have time for here, but to show you a bunch of examples. But there's a lot of times where actually you can partition your system. I went off my script here a little bit, but I should have prepared a simple example of showing you how you could do this for the pendulum, right? So you can take the true dynamics of the pendulum, you can linearize them, and then you can bound the difference between the nonlinear system and the linear system by some worst case bound delta. But you can say that if the gain from here to here of the delta system, from here to here of the delta system, is somehow multiplied by the gain from here to here, if the total loop gain around here is less than 1, then the whole system will be stable. That's called the small gain theorem. Is that the loop gain stays less than 1, implies stability. And you can just analyze an existing system the way we did with Lyapunov, and you could find, a dissipation sort of inequality, which is like a Lyapunov function that proves that each of these is bounded from W to Z and from Z to W on the other side. Or you can do H infinity design, where if I have my other U and my X coming out, for instance, I can ask the question, can you find a matrix K such that the whole system that makes the top system, the whole system then becomes stable? And that's the H infinity design question in its full glory. Okay, and in the limit, in the simple case that I showed in lecture, W was Gaussian, Z was just my LQR, my square root of my LQR cost, basically. And I gave you the derivation with the Riccati equation to find K. And there's a bazillion more ways you can wire it up to do good things. So in some ways, I want you to see this as almost exactly what we've talked about before. But I do want you to appreciate that there's one big nice difference, which is where we've extended our notion of input to state stability, if you will, or just even state stability for Lyapunov analysis, to sort of input to output stability with a dissipation inequality and a L2 gain. And that allows you to start composing systems in a really nice way. Questions about that?
Maybe it's synonymous to one of these tools that you just mentioned, but there's one tool called loop transfer recovery. Is it synonymous to one of these that you mentioned? Or
Yeah. So
how does it relate?
Yeah, that's a good question. There are a bunch out there. I should know exactly what loop transfer recovery is. Yeah, I don't know exactly where that. I just don't want to say the wrong thing. I mean, there's a lot of things that are connected. Like for single input, single output systems, you can accomplish effectively the same thing with loop shaping kind of arguments and other classical linear design approaches. And in some sense, you could think of this as the extension to high dimensions and multi-input, multi-output kind of systems. Dongchen, do you know loop transfer recovery? Do you know that one by name? No, I'm sorry.
No, yeah, I don't recall.
Yeah, I'll look it up and answer. So there's loads and loads of literature and work, and you might have heard of mu synthesis, which again is, yeah, I wonder how close loop transfer recovery is to mu synthesis. But there's a lot of extra work you can pile on if you need more structured uncertainty descriptions in order to find a good bound. So right now, this is a relatively weak description of the uncertainty, which is just to say that, I've choosing some total, it could be arbitrary, random, but it's just the total integral power in the signal is finite. There are more structured forms of uncertainty that you could write. You could say, for instance, I won't just rattle them off for you, but in particular, in this system where you have, the output of this delta box is really not some random IID kind of system that has some bounded power. It's highly correlated. It's probably just a static function of your input Z, right? So this is a case where a different uncertainty description of WN and thinking about structured uncertainty and what's the gain of structured uncertainty through this can give you tighter bounds. Okay, so there's loads of work and functions you can call in the robust control toolbox in MATLAB that are for the structured uncertainty case, and they are just adding on to the richness of this toolbox. They can give you gain bounds for systems that would not have a gain bound at all for the generic uncertainty description, or they might give you a tighter, smaller gain answer than one that's asking to be robust against everything. Cool. Well, I don't want to talk too much longer, but there's lots to know here, but I hope that gives you sort of the high level idea. I spent the day writing up some more of these notes, so hopefully there's and I'll try to make more progress tonight. I think there's a little bit to know that'll give you a lot of context when you're reading through. And I don't think people know enough about this, or I think a lot of the newest work in robotics and RL isn't making full use of the power of this toolkit. But there are some new results in machine learning that are contributing back to these kind of results. So in online adaptive control, online optimization and the like, there are new results from machine learning that actually give tighter bounds than we had before from just control. So let me just compare this. I'll just end by comparing this to domain randomization in RL. And there is sort of a canonical picture that Peter Beal and company put in their first paper about domain randomization. Right, so the way that people are trying to get robustness out of their systems in RL these days, especially if they're trained in simulation, is you start adding lots of different disturbances in simulation. Now, sometimes they can actually be disturbances in the sense that I might have measurement noise or disturbance inputs. Sometimes they are changes to the parameters, like the lighting conditions or the texture map of the object. Okay, you should think about all of these in some sense as being a simulation-based way to write down W, right? To write down some disturbances. And effectively, what people are doing is they're asking their system to be robust against all of these different disturbances. Typically in RL, our objective function, not always, but typically in RL, our objective function is to minimize the expected value. So that's really a lot more like the stochastic optimal control, where I think we can understand sort of completely in the LQR case, and we know that how it gets hard in other cases. Because I mean, the big thing is, does your distribution stay Gaussian or does it not, right? As soon as it's not, it's like arbitrarily complex. And these are certainly not in the linear Gaussian regime, like someone's flipping the lights on and off and I've got a pixel bit to torque-based controller. Okay, so in some sense, it's a little hard to think about this with the classic tools. But at the same time, the tools, I think thinking clearly about them in linear systems can tell us a lot about what's happening here. So, well, first of all, if we're only optimizing the expected value against these disturbances, then there's really no guarantee of how well they work against, you might put in a disturbance that was inside your, your training set, and the response could be arbitrarily bad. That's something we know. That's the classic John Doyle abstract that says, what are the stability margins of LQG? And there are none. It's like, right, we talked about that. Similarly, if you were to do robust design against this, right, one of the great things about robust control, I think, for linear systems, is that if you say, I want to be robust to this set of this amount of disturbance, right, or achieve a certain gain margin, if the system, because these run through convex optimization in most cases, if the system might just say, no, you can't do that, right? And there's a well understood sort of trade-off between the amount of uncertainty you're pushing into the system and the control authority you have, right? So at some point, if you're putting loads of uncertainty in the system, then your system needs to have a lot of control authority in order to reject those disturbances and still give you a reasonable result. So when I first started seeing the kind of flipping the lights on and off, putting cheetah patterns and everything on the robots, that meant to me that the tasks we're asking these systems to do are relatively easy, or somehow the robots have a lot of control authority, right? And I think that's not a criticism. That's just saying that if anything, it's a good thing, right? It's that I think like a lot of the manipulation tasks we're trying to do right now are sort of not like the hardest problems we've been talking about in this class, where you really are riding on the edge of control authority, or you're very underactuated, and you really have to reason about the dynamics. It's kind of like, my mass could be 1, it could be 100, it doesn't really matter. I've got enough control authority to get the job done. It seems that we're in more of that regime right now in a lot of the RL examples we're seeing. And I expect that there's a future where we're trying to eke out the last bits of performance for the system, and we won't anymore be able to get away with asking for random, robustness to every possible thing. And we'll have to get more specific, more nuanced with our description of the uncertainty that we ask to be robust against. And that's a super interesting question, right? Like, how do you write distributions over, the kitchen sink or something like that? How do you write that distribution so that my manipulation system is dialed in, it's operating at the limits of its performance, it's not trying to do, I don't know, tying shoes and kitchen sinks. It's like dialed into kitchen sinks, and it's really, it's rocking it. I think we're not there yet. We're not doing that, except for when we're doing empirical. If you're doing online RL, maybe, then you can dial into the exact system you're doing, and that's expensive, but that's maybe the dream. So that, I think we're in a great place where we're trying to walk that line between sort of offline training against poorly, because it's hard, poorly crafted distributions, and sort of like online optimize exactly the true distribution from the world. Oh man, I'm so bummed I just saw the chat, but let me read it now. Yeah. So we've focused on linear systems here, mostly because I believe that's where clarity can be found. Does anything change when we go back to nonlinear systems? So the Lyapunov arguments I talked about, the dissipation inequalities arguments I talked about, you can use that machinery for nonlinear systems. You might need more than a quadratic Lyapunov function or the like, but the machinery still works. I think the biggest question, the synthesis tools are weaker. You have to do, things like sums of squares or gradient descent or something like this in order to make similar statements. And in general, they don't work as well as the convex linear cases. But there is a question: is L2 gain even a reasonable thing to ask for nonlinear systems, right? Because in the same way that it's sort of bad to ask a linear system to try to stay in some bounded region when it just doesn't want to do that, it might be wrong to ask. There's certainly some nonlinear systems where you just don't want to ask them to be a simple gain times the disturbance, right? It might be that they're going to do arbitrarily bad things at the edges, and the L2 gain might not be the right question to ask anymore. And so, I think we can talk about regional certificates, and that's one way to fight that complexity. But in general, I think we don't always know. There's not like nonlinear systems are kind of like, anything else, right? So, so I think there's not one great answer for what's the right way to ask for robustness for them. Cool, AJ, why don't you hit it, and we'll take any other questions that people want to ask.